What's up everybody? My name is Jesse and welcome to the first video in a series in which we recreate Pong using C++ and SFML. We will be using C++ because it is a fast, powerful language that is perfectly suited for game development, alongside SFML, which is an amazing library that will allow us to create a window, get input from the player, and draw our game graphics, as simple as they may be. In my videos, I will not only be showing you how I code, but also teach some coding best practices and professional development skills that are useful for everyday coding in a work environment. I will do my best to explain my workflow and the decisions I make along the way, but if you have any questions, please leave a comment below. Pong is a very simple 2D game that contains a playing field, a ball, and two player control pedals. The aim of the game is to get the ball to go behind your opponent's pedal while not letting the ball go behind your own pedal. So normally, if this was a professional project, we would specify how this game works before we started coding. But I'm going to let that slide this time and assume everyone knows how Pong works so that we can get along with recreating it. I'm currently using Ubuntu Linux. Let's begin by creating a directory for our project. In most operating systems, you can create a directory using the make directory command and navigate into it using the change directory command, also known as cd. With our directory now created, let's use git to initialize our directory for source control. Any coding project worth doing should have source control. I will be using CMake to help build my project, and I like to start with a simple Hello World app to ensure everything is working correctly. I use NeoVim as my editor of choice and usually like to work from the command line. If there's enough interest in my workflow, I will consider making some videos explaining my Vim configuration. We have the Hello World code in place now, so let's attempt to build our project. Let's first create a build directory and navigate into it. To get CMake to work with our project, we need to run the CMake command and give it the directory with the CMake lists file that we created. CMake was able to generate a build system for our project currently, so we can attempt to build our app now. Building the app is as simple as calling the make command from within the build directory. If you would like to know more about CMake, there are lots of resources online, but I would recommend Jason Turner's Intro to CMake, which I will link to in the description below. I'm going to need to compile this project every now and then, and I'm not a fan of having to close my editor each time I need to do that. I use a tool called Tmux that allows me to create multiple terminals and easily switch between them. I'll start up Tmux in our project directory and create a terminal window that we can use to build and run our app. I'm going to rename this terminal window to Run and rename our initial terminal window to Editor so you can easily follow me as I switch between terminal windows. As I said earlier, we'll be using SFML to create this game. I don't yet have SFML installed on this computer, so let me just install it by using my package manager. If you are on Windows using Visual Studio, you could also obtain SFML by using the NuGet package manager. CMake makes adding libraries to a project trivial with the target link libraries command. We will need to link the SFML graphics, SFML window, and SFML system libraries. Let's now use SFML to create a window. I'm going to use the SF namespace so that our code looks less cluttered. I do know that we need a render window class to create a window that we can draw to in SFML. What I can't recall is how exactly it is constructed. Thankfully, those are not things that we need to remember. Let's just navigate to the header and look at the constructor. The render window class requires a video mode and a title string. The rest of this constructor's parameters have default, so let's not worry about those just yet. We only need a video mode and a title. Let's see what exactly a video mode is. Video mode seems to describe the window's width, height, and bits per pixel, but because this has a default value, we will ignore it for now. To create a render window, we only really need the window's width, height, and title. With our window now created, let's use it. We need to create a game loop in which we handle user events, update our game state, and draw the game. Let's create a while loop that will run as long as our game is running. We can use the Windows isOpen method to determine if our app is still running. We then need to handle user events. For the moment, the only event I want to deal with is if the window was closed. And in that case, we will call the Windows close method. We don't have any game state to update, so we will skip that step and move on to drawing our game. We don't have anything to draw yet either, but we should be clearing our screen and calling Windows display method to show its content to the screen. Let's try to build and run our project. If you're following along, congratulations, you have a symbol window displayed. We've made our first steps towards creating something. The last thing I'm going to look at is the performance of our Pong game. If I bring up my system monitor, I can see that the Pong app is using 8% of my processor's power. I have a 6-core, 12-thread CPU, and if I'm not mistaken, 1 divided by 12 is just a bit bigger than 8%, which means our simple app is using all of the processing power of a single thread to run this simple game. The reason why our app is doing this is because the game loop is currently running as fast as it can. This is unnecessary. We only need to run as fast as our monitor can refresh to ensure a smooth gameplay experience. We can do that by enabling vertical sync through our window object. Now when we run our app, we will see that it's using very little of our processor's power, which is just what we want for such a simple game like this. Vertical sync causes our game to slow down by causing the Windows display method to sync up with the monitor's refresh rate. So if the monitor is not drawing a frame at the moment, it waits until the monitor is ready and then sends the frame to the screen. This wait causes our game to run just a little slower, but also not use up an unnecessary amount of processing power. With vertical sync enabled, our game loop only runs at 60 frames per second on my setup at least, which, as most gamers know, is the standard for game frame rates. Before we do anything else, let's commit our changes to source control. We don't need to commit our build directory, so let's add a .gitignore file to our project and ignore the build directory. With that in place, we can commit our changes and wrap it up for this video. Thank you for following along, and if you have any questions or comments, just leave them down below.